Alright, suppose that this polynomial ring is Noetherian. We want to prove that the underlying ring is Noetherian as well. This is the converse to the Hilbert basis theorem, and it's usually not mentioned because the Hilbert basis theorem is so much more difficult that algebraists, like, I don't know, I think they typically don't even bother to mention this, even though they should, because it's important to know, I guess, if they care about these kinds of things, which I guess they do if they write theorems about them. But anyways, so let this be an ideal in A, let fancy A ideal in A. You can prove that taking this ideal and adjoining X is an ideal of A, and I'm not going to go through the detail, but to verify that this is an ideal in the polynomial ring, basically what you do is you have to take sums in here and prove that they stay in here, and then you have to take elements of AX and multiply them by elements of fancy AX and prove that you stay in fancy AX. And what you do when you multiply these things out is you just combine a whole bunch of coefficients of these polynomials, and then so when you're just adding two of these together, then you're adding together elements, and the coefficients are going to be elements in this ideal, and since the coefficients are in the ideal, the sums will be in the ideal, and so you'll be good. And then if you take this fancy A and multiply by an element in the overall ring, then if you look at the coefficients, what you're going to be doing is you're going to be taking elements, the coefficients, some of them are, you're going to have elements in this ideal multiplied by elements in this ring. And since this is an ideal in this ring, multiplying by arbitrary elements of the ring will keep you in the ideal. And so, in fact, it is the case that this is an ideal in here. It's just everything will work out in the coefficients because the coefficients are elements of an ideal. Anyway, so that's that. The other thing is that if A is contained in P, then obviously this polynomial ring is going to be contained in this polynomial ring. So anyways, suppose that this polynomial ring is Noetherian. Now let this be an ascending chain in A. We want to prove that A is Noetherian, i.e. we want to prove that this chain terminates. So just put x's on everything, then this gives you a chain in AX, and by Noetherianity, this chain must terminate. And if this chain terminates, then the first one must terminate as well. And so A is Noetherian, and that's really all there is to it.